Right, hi guys, and welcome to lesson 5. As you probably noticed, now we're getting a little bit further in the course. Lessons 1 to 3, I looked at some binary, some twos complement stuff. Really, kind of, just a tiny scrape of the surface of, you know, um, what will be, binary arithmetic. Yeah. And then in lesson 4, I just had that sort of metal background, and I came up with 42 Java tips. Now, obviously, I'm going to be using, because I'm doing Java, we'll look at various IDEs. The one I'm probably going to be using mostly will be TextPad with NetBeans possibly as well. Eclipse, I don't think so. So that's just, it's going to be mainly TextPad, and maybe later on we'll be looking at NetBeans. So just so you know what, I'm going to be looking at, I think games is probably the best thing to do here. But obviously with the computer architecture side of things, we need to really kind of back up all these, we need to look at all the functions. Anyway, so let's just start anyway. Okay, that wasn't supposed to be there, but oh well. Anyway, so did I even, so I think we can just put that in there, maybe. Put that in there. Yeah. And when it grays out like that, then it's a comment, and I think that's the comment notation. Anyway, so no, it is. So 7x. So we assign 7x to 55 there. And tag times in 7x is protected. Well, I'm sure we'll find out what that means, but don't worry, they get better than this. So we can do this. 77 squared is 5929, and then when we use the percent sign, we're referring, I believe, to the previous answer. It may actually be, and I think you can actually, and it actually, looking at one thing I didn't do was to, if you use the percent sign twice, you can get the answer before that, and you can also use the line number. You can't actually see the line number, but in the actual, when you actually type it, it will have like in like number, and then in square brackets it will have like 1, and then close square brackets. And then the output will be, and that gives you a good way to see the sequential order of operations. But yeah, like I say, the amount of percent sign, you just take, if there's, there's k percent signs, then it's the kth previous result. So there's that, and as you can see, I've done that, and then we put that, and then here we have pi. This is we have to specify the level of precision that we're going to be using. So once we've set the variable pi to 100 decimal 100 places, to 100, is that 100 decimal places or 100 significant figures? I think it's And the thing I'm looking at, it says 100 digit accuracy. So I will. I could actually just no, I wasn't actually. No, I'm not going to do it now because it's going to get in the way. But yeah. Anyway, so I'm just going to read through it. It's not going to look quite like this when you type it in. You will need to use you need to use some stuff. And there we have this. Seems to be to indicate line break. Anyway, I suppose you can count the number of digits and you can see exactly if that's 100 significant figures or 100 decimal places or what. I'll do that. Off cam, I think it's a waste of time really to do it on cam. Then we can set it to x, and then the variables are permanent. So yeah, you're setting the variable, and then this notation here, x equals, and then just a full stop. That will clear x. So x is no longer 10, and that will produce no output. So then when we move on and we say we set to 48 here, and then we do this. What does this mean? I don't even remember what it means. I think you can kind of tell what it means. It basically puts x equals 20. Yeah. Yeah. Essentially, what it does. Let's see how you can think about it like this. So x goes to 3. Yeah. Clearing x as it goes to 3. Let's see what I wrote here. Yeah. Yeah. To apply transformation rule to a particular mathematical expression, you type expression and then /rule. And then the replacement operator /dot is typed as a pair of characters with no space in between. And you can replace x with any expression. So yeah. But yeah, I mean obviously yeah, I put it as 20, then that's doubled it and added 1. Come up with the answer. And it's just trying to look at the input and the output really. You can see I've set up some variables here. Yeah, you know, look at that dot, yeah, /.x. That's the thing. It's a transformation rule. X goes to 3. So take an expression such as 1 plus 2x and replace. Yeah, okay. Yeah, I need to look at this. This is yeah, really look at this stuff. It's important, that stuff. Yeah, I know I'm supposed to be teaching you, but yeah, everyone has to learn this stuff themselves anyway. So I got a bit bored there, and I did some fairly obvious things. And then we came to a list, and we set the list up like this. Now I decided to have, what was it? Yeah, this isn't really a proper list, is it? There's some sort of mix between odd numbers and Fibonacci. I don't know why I thought of that, but that's what I thought of. And then we applied square plus what, you know, we took every yeah, we basically squared every value in the list and added 1 to it. And then we came up with that, and then we did some more hardcore stuff did it to the power 4 to look at what the answers would be there. You know, these are actually quite interesting answers, some of this. And I went even further into it, went to a tenth, and I went over to the half. You know, and these are quite interesting answers, so, but you know, you have to really look at them, you have to think about, you know, what's going on algebraically. And then another function, yeah, so we'll put half to 10 decimal places, to a precision, yeah. So I shouldn't really say it, to a precision of 10. And then we get onto this mission, and then for some reason, I think this tells you the floating point, and I haven't even got into this yet, but this tells you the floating point accuracy of your computer. So is that good? Probably not. 7.97729488509550169. Okay. Yeah, once you make a mistake, that's when you stop, because now it's not going to make it. And then what do we do? 2 to 1001. That's quite a large number. And then 2 to 1000. It's interesting, isn't it? That 2 to 1001 starts with 2, 1. And then 2 to 1000 starts with 10. 2 to 990 starts with 10. 2 to 880 to 980 starts with 10. And yeah, even these very big numbers, you find it's really strange to me, especially with, you know, and then moving on anyway from that, we can express obviously we can express binary numbers. We can this is conversion. In a sense, this actually may be a good way to you know, when we come up with the next algorithm for, you know, the next questions that we spoke about in the lecture, in lessons 1 to 3, we can focus on more digits here, and yeah, we can obviously I'll start incorporating some of these conversions, you know, directly into the answers. So maybe we can actually get through a bit faster as well, because doing one question for each lesson is overkill really. So there's up to 6-bit now in base 2, and you can obviously use any base. Here we do it with, you know, you can see a 4-bit hexadecimal number. Yeah, you know, that's how many values you've got. 0 to 65535, I suppose. And then we just did some more interesting stuff. We looked at how 0FFFFF is, you know, kind of gets there, doesn't it? It's kind of 1/16 of the way there, is it? Yeah, it looks about it. Well, you know, it's obvious it is really. When you think about it, and just by the amount of, you know, pounds of 2 that you have to go to get there, to get into the next, and you know, think of branching and stuff. And then there's just some more interesting results. You know, it's a little bit confusing, the results, I can tell, because what it does, it kind of gives you output for, like, it wants to keep that, it wants to keep the number because you know it's doing something to it. So sometimes it does the output. This is obviously not really that accurate, what I'm saying, but in a sense, you basically get 2. You know, when you enter one of these things, you get 2. You know, and that's why, you know, you should ignore the stuff not in bold. Anyway, that's about it I wanted to show you for that. So yeah, we'll continue with this in another lesson, and we'll also start looking at some, you know, I realise it's very powerful, this language, actually. So I will be, you know, sort of learning it alongside, you know, bracketing. There's a parentheses for grouping, and square brackets for functions, curly brackets for lists, and then double brackets for indexing. Yeah. So normal brackets. Yeah, I mean, that's the thing. Now, I don't really like this term curly braces. Why not call it curly brackets? You know, it seems to be wrong, really. So I'll be calling it square brackets, curly brackets. I would also use double brackets as well. Sequences of operations. Yeah, you probably noticed that in earlier stuff. Where did I do a sequence of operations? When I listed the variables, we put a semicolon between each. Can't actually find it there. Yeah, you see, this was our notation. We just put in Z space equals space 5 semicolon space, and then Y space equals space 10 semicolon space W equals, and then space, but anyway, but that's the way to look at it anyway. Anything else? Once you put a semicolon at the end of the line, you don't want an input, you don't want output rather, sorry. So once you put that semicolon there, you're saying you don't want any output. If I put a semicolon at the end of this 20 here, there'll be no output. I could use the percentage sign to get the output though. Lists, the value of percentage sign is the whole list there. And like we showed you before, you can apply the function to every value in the list, which is nice. And there's differentiation as well that we'll go into. But aside from that, that's kind of basic calculations. So thanks for watching.